Okay, let's start. Good morning. So we have about, we have exactly 8 classes left for new material. So this week, 4 classes, and next week, 4 classes. And then we're going to have week 15. We have 2 classes in week 15, but those are reserved for review for the final. And so in week 15, Wednesday is reading class, and I think our final is scheduled to be on Friday of the week of 4/21. And so that'll be it. And I would like to be strategic about my time left. There's so much more to cover, of course. This is just the beginning about series and stuff like that. And when it comes to representing functions as series, it's a whole subject that is like beautiful and stuff like that. But and even when it comes to numerical series, we said that there are 2 main questions, right? So if you have an infinite series, formal series, there are 2 situations, 2 questions. One of them is, does the series converge? And the second of all is that if it converges, can you compute the limit? And at least for answering the question of convergence, there's a bunch of tests. And we're going to discuss some of them today, and possibly we're going to discuss some more tomorrow. But probably I'm going to de-emphasize them a little bit. I would like to leave it, leave this whole like topic of series of numbers, however far you can go this week. And then next week, maybe 1 or 2 classes, I'm going to talk about power series and analytic functions. But what is more important, as far as I'm concerned, is this Taylor approximation. We had talked about, because I feel like that is more thematic to this class, we had talked about when it comes to differentiability. Differentiability was, in essence, equivalent to locally being able to approximate a function by a line. And Taylor approximation tells you sort of a higher order version of this. If you have two derivatives, you get to approximate using a parabola and so on. In my experience, that is more applicable for more people. So I would like to do justice to that. So probably we're not going to be covering in great detail this idea of real analytic functions. Okay, so I'm going to take attendance today. Are there any questions before we start? Now, let me remind you, we had started talking about expressions of this form, and initially we were like, okay, so I have a sequence of numbers, and I'm looking at their infinite formal sum. And initially we said that when we write it initially like this, we would like to be able to write it like this, and if possible, then investigate if this thing makes sense. Okay? And that's why, if you look at this expression without any sort of concern about its convergence, we call this a formal series. And then what we did was, we said, oh, we're going to say that this actually makes sense. That is to say, this is convergent if the sequence of partial sums is convergent. In which case, the limit is going to be the definition of this. You see, this is a sequence now, sequence of real numbers. And if I had started with functions, this would be a sequence of functions. Convergent. Then this expression, which initially was a formal expression, is defined to be the limit of this. Okay. Now you might say, why then just not stick to the notation for sequences? Because we've been dealing with these for so long, and we have these limits of sequences, maybe S sub n, blah, blah, blah. Why even bother writing something like this? I think fundamentally it's a psychological sort of psychological thing. So, because for instance, if I wanted to think about the convergence of this, somehow, maybe because of tradition or whatever, it's easier to think of it like this infinite sum that happens to converge to this special number E, than to say, okay, so I just have some number sequence defined like this, and E is the limit of this thing. Somehow, perhaps, this is more familiar in a sense. It depends, of course. And we had discussed how there is no fundamental difference underneath the hood between a series and a sequence by way of this discrete fundamental theorem, right? So we had discussed for the discrete fundamental, by way of the discrete fundamental theorem of calculus, you can think of this as the analog of this. So let's say 0 to x, f of t dt. So this expression is an analog, discrete analog of this. And just like I can go from a sequence to its sum sequence, I can differentiate in the discrete sense to start with a sum sequence and get back the original sequence. So they are sort of, you can transform one into the other one. Somehow, this is more traditional. Okay, so this was sort of like a review. Here's an exercise. I have a sequence of real numbers. Then this series converges, which means this, literally means this, if and only if the tail sequence or tail sums converge to 0. Right? This looks like it is sort of like a circular thing, because I'm saying this makes sense insofar as this expression makes sense, which is true, which this exercise requires you to verify as well. But ultimately, what this says is that if you're sort of adding infinitely many terms, well, the tail, right? So if you concatenate the remainder after the first n terms, that tail, as you're taking the tail to infinity, it should go to 0. Otherwise, it wouldn't be able to stabilize. So this is a nice exercise. Here's a theorem. It's not very complicated, but it's going to allow us to sort of transition into this comparison test, which is the mother of all tests as far as I'm concerned when it comes to series. And it's going to help us sort of get back to something that I promised we might prove like 2 months ago, and we had skipped it at the time. But we're going to have to discuss that. So here's a theorem. What did I call this? Okay, I call this the tail criterion also. In a sense, this theorem is a finitary version of this. Okay, so instead of looking at the total infinite tail, I would like to look at some finite tail. I take a sequence of real numbers, then the series converges, if and only if, now is the epsilon delta statement. For any epsilon, there is an n, capital, such that for any n after capital N, and for any p, positive or non-negative rather, the sum from n to n plus p in absolute value is bounded by epsilon. So this is a finitary tail. Okay. Does any of you remember a condition like this before? We didn't spend too much time on this style of epsilon delta stuff. But in a sense, for any epsilon, I'm fixing a time, and I'm comparing two different times, n and n plus p, after this capital N. So this had to do with so-called Cauchy sequences. Okay? So I'm going to first do the proof, assuming this theorem that we had discussed 2 months ago, that I didn't prove at the time. So first I'm going to prove this theorem, assuming the previous theorem, and then I'm going to prove the previous theorem, because now it's time. As usual, in order to make this infinite series workable, let's say, first let me define the sequence of partial sums, because the convergence of this is all about the convergence of this other sequence. Okay? Put for any n, let's say S sub n. So this is going to be the finite sum from n to 0, 0 to n. Then the series converges if and only if S bullet converges. S bullet itself is a sequence of real numbers. The definition of this literally is the convergence of this. And now we use this theorem I was alluding to. It turns out that a sequence of real numbers converges if and only if it is Cauchy. It's a Cauchy sequence. Okay. So we're going to have to prove this. It's a Cauchy sequence, and this by definition means let me be faster here. For any epsilon, there's an n, such that for any lowercase n after uppercase n, and for any p, the difference between the nth term and the n plus pth term is bounded by epsilon. And then writing this out explicitly gives me that so this is the sum from 0 to n. This is the sum from 0 to n plus p. So if I were to look at the absolute value, this would be the sum from n plus 1 to n plus p. Which, of course, I can rearrange these indices to get exactly this statement if I wanted. This should be lowercase n, by the way. Okay, and that's the end of the proof. Okay, so what remains to be proven, which we're going to use in the next theorem as well, is this red star. And initially, the reason why I didn't spend too much time on this is that convergence of a sequence, let's say in a metric space, is one thing. Cauchy property, even though they are very similar looking, is a different thing, and they sort of belong to different contexts. And so I didn't want you to sort of confuse those two contexts. That's why whenever we had something to do with Cauchyness, or uniformness, for instance, we had skipped it. Remember, I think last week too, or the week before, we needed to prove something, and we needed, for that proof, for the Riemann integral, we needed that any continuous function on a closed and bounded interval is uniformly continuous. So uniform continuity and Cauchiness, they belong to the same context. They belong to the uniform world. Okay, so let me write this here. Two different contexts. One context is what is called the context of topology, okay? Science of place. So things like convergence, continuity, these are in the context of topology. Any other? And the other context is the uniform context, or uniformity if you want. This is when you have uniform convergence, Cauchy sequences, uniform continuity. Or maybe I shouldn't say uniform convergence actually. And this is another thing that is somewhat confusing. Uniform convergence, say, of a sequence of functions, it really belongs to the first category, okay? It's kind of confusing, and that's why I don't want to sort of spend too much time on this. Uniform convergence is a much more broader thing than this stuff. Uniform context is really a special thing. And so this red star is about the uniform context. And so now I need to prove this red star. Did you all sign the attendance? Okay. So, it's an if and on if. So we need to prove both ways. Of course, the reason why these are sort of confused is that whenever you have a metric, you have both. Once you have a metric space has a natural topology and a natural uniformity. So you get to talk about both. Okay. So maybe I should draw some picture about this because at the time I didn't spend too much time. So when you're talking about a sequence converging to a point, right? The convergence of a sequence, that's an absolute thing. You have a target, okay? You have a specific target, which is the limit. And so okay. You have this target. And then you have a bunch of points, okay? In your space, your x bullet keeps moving. Okay, maybe it does this many times, and then maybe it does this, blah, blah, blah. But convergence at this point, I hope you're familiar with these ideas, means that you get to approximate this target arbitrarily closely using terms from your sequence. So what does this mean? So ultimately, really, you want this guy to be equal to this. You really want this to go there, but that's too much. And so you say, okay, let me just ask for arbitrary approximation. And you say that if I were to take an epsilon ball for any epsilon, if I wait long enough for this capital N, eventually this thing is going to stabilize and it's going to keep moving inside this. It's not going to escape it. Okay, this is what it means for convergence. And then, of course, you can shrink epsilon to perhaps epsilon over 2. Then maybe you need to wait longer. But convergence means that if you wait, again, long enough, you're going to be able to stay within the smaller ball also. So you wait, and it's like, eventually it stays in this. And then you shrink epsilon even further and further and blah, blah, blah. So in the limit, S bullet basically stabilizes to S infinity. Okay, this was the idea of convergence. And of course, we had a subsequence converging. That was a different matter, right? So when you were looking at the subsequence converging, this is also like a review for the final if you want. For some time, you could capture your terms within the epsilon ball, but for some other times, possibly the sequence escaped still. So what we could do is we could sort of sample out those bad times to stay within the epsilon. That was the business with subsequences. Okay? This is just review, but I'm sort of reiterating these ideas because there's a disconnect between sort of sequences and metric spaces and infinite sums. Really, as I'm sort of like preparing these classes, I'm realizing my psychological access to these objects is very different. Maybe it shouldn't be, but so this is convergence. Now, when it comes to Cauchy property, now it's not an absolute thing. You don't have a target. Okay? So let's do this. So if for any epsilon there is an n such that for any n after capital N and for any p, s sub n minus s sub, well, let me just use distance. Distance between s sub n and s sub n plus p is bounded by epsilon. Now you see I don't have the target yet. What this is saying is something about volatility. What this is saying is that if I wait long enough, consecutive terms of my sequence are not going to wiggle too much. They're going to be within an epsilon of each other. I'm not saying where it converges to, you see. There's no S infinity here. So now the picture is something like this. You see, I cannot put my target and look at the epsilon ball around it because there is no S infinity here. So it's a relative term in a sense. But what this is saying is that maybe initially this is my sequence. But if I wait long enough, the oscillations, so to speak, are going to be within an epsilon. And then if I wait even longer, the oscillations are going to be even lesser. Okay? Now, again, we would like to take epsilon to 0 to say that eventually this actually stabilizes so that there's a limit. In other words, we would like to say that the Cauchy sequence also is convergent. And this is the content of this red star, you see. It turns out that this is true, but this is where you used, maybe I should ask you, there's one axiom that we use here. What could help me here? Let's say that I have a sequence whose volatility sort of decays in time, but I want a limit. How can I guarantee that there has to be a limit there? Heuristically speaking. So there was one of these axioms that guaranteed that certain numbers exist, certain things exist. So you don't fall out of the space within which this thing happens.
Is it the one where between any
Yes, but that's not quite the thing. I guess you're getting closer. It's what is called the completeness axiom. Any set, any bounded set has an infimum, supremum, all that stuff. This is not exactly the same sort of completeness, but it turns out that they're very closely related. Okay, so this is the intuition. Once you have decaying volatility, in other words, a Cauchy sequence, if your space is complete, that means that in the limit, you're going to be able to find a point. In other words, such sequences that oscillate less and less in time are going to have to converge somewhere. They're not going to fall out of the space. Okay. So this was some heuristic. So let's prove this red star now. This was like a short review as well of the sort of first things that we discussed in this class. I just wanted to reiterate how these ideas sort of come back, and really it's like we had to cover those things. And it's kind of shady at this point, or you're sort of somewhat shaky about these kind of things, and that's sort of like the nature of the thing. Clearly you forget and all that stuff, and then if you keep studying these kind of things, eventually it's going to become second nature. Okay, so let's start with this direction. If it converges, if a sequence of real numbers converge, it has to be Cauchy. Well, let epsilon be positive. Now, what is the idea? I know that even though this is one-dimensional, I'm going to draw sort of like a two-dimensional picture, because somehow I feel like two-dimensional pictures are more intuitive. If this guy converges to S infinity, let's say, I know that after finite time, S sub n and any other term after 2 is going to be within an epsilon. Okay? But then if both of these are within an epsilon to S infinity, or let's say epsilon over 2 perhaps, then that means that the distance between these two is bounded by epsilon, because they're in the same bowl after all. So this is bounded by epsilon. That's the idea. So let epsilon be positive. There's an n such that for any lowercase n after uppercase n, I know that S sub n minus S sub infinity in absolute value is bounded by epsilon divided by 2. Well, if if lowercase n is after uppercase n, then so is lowercase n plus p. P is a non-negative number. And so by what? By something, I can get from here to there. So in this picture, what I'm saying is that this distance is at most epsilon, and this distance is at most epsilon, epsilon over 2. And I want to say that this distance is at most epsilon. What can I use here? Yeah, there's a triangle. There you use a triangular inequality, which says that this edge in length is bounded by the length of this plus the length of this. This is less than epsilon over 2, so is this, which means that this is bounded by epsilon. Okay? So that's the easier part. Any questions about this? Okay, let's do it the other way around. So if I assume that S bullet is Cauchy, now things are slightly complicated, because somehow I need to find a limit. Okay. So the other way around. Now, what are let's remind ourselves, what are the types of theorems that guarantee that a certain thing, certain limit exists when it comes to sequences? So for instance, if I have a bounded sequence, can I deduct that it has to converge? So for instance, -1 to the n, this is bounded, but it doesn't converge. But of course, it has a convergent subsequence. Now, is there a theorem that maybe up to a subsequence guarantees that I have a limit? After all, in the case of Cauchy sequences, I don't have the target. Somehow, I need to refer to something to get that target. Right?
Weierstrass.
Okay.
I think does this.
Yes. But do we know that Cauchy sequences are bounded? It turns out that they are. Because when you think about it, Cauchy sequences are asymptotically sort of non-oscillating sequences, if you want, which means that eventually within an epsilon, they're going to have to stay in some epsilon ball. So let S bullet be Cauchy. So if I were to use epsilon equals 1, for instance, there is an n such that for any lowercase n after uppercase n, and for any p, the difference between s sub n and s sub n plus p is bounded by 1. I don't need to take epsilon to be very small here, because I'm just trying to see that it is bounded, in fact. So what does this mean? So if I were to choose lowercase n to be this uppercase n, which is a fixed number, fixed time, that says that after uppercase n, all of my subsequent terms is going to be within 1 of this s sub n. So I don't know initially what happens. I have finitely many terms, right? So I started, let's say, at s sub 0. Here I have s sub n. And of course, I have infinitely many more terms. That's the nature of a sequence. But what I know is that they're going to be within 1 of this term. This is not the limit necessarily, but at the very least, the sequence is bounded. Okay. Now, like your colleague suggested, Bolzano-Weierstrass guarantees, that's the content of Bolzano-Weierstrass, guarantees that any bounded sequence of real numbers has a convergent subsequence. There is a j increasing, strictly increasing function. Let me be explicit, perhaps. Such that if I were to define, for instance, t sub n to be s sub j of n, so that T bullet is a subsequence of S bullet, such that, and there's a T infinity, real number, such that T bullet converges to T infinity. So you can sample out certain times from your Cauchy sequence that converges to something. Okay? What is it? I don't know at this stage, because Bolzano-Weierstrass is sort of like a black box in a sense. We had proved it at the time, but it doesn't really tell you what that value is after all. But the final step I'm going to leave to you, namely that the final step is to show that in fact this S bullet converges to this subsequential limit also. Exercise. This is a very good exercise. I highly recommend that you do this. Which I hope makes some intuitive sense, because I have some Cauchy sequence, which means that eventually it doesn't oscillate too much. But within that, I sampled out certain times that actually converges to something. But then that means that the whole sequence should be anchored around that sequence, or around that subsequence. Right? So this is my S bullet. And then somehow I sampled out these special times. So something like this, perhaps. And I know that this green sequence, which is T bullet, converges to something, T infinity. But eventually, the oscillations are going to have to decay faster and faster, or decay more and more, which means that the original sequence has to converge to where this subsequence converges. That's the main idea. I'm going to leave it to you to formalize this idea, but this is a very nice exercise. Okay. Okay. And we had said that, so you can, I hope, anticipate at this point, really we're not using anything about the real numbers. We're using the completeness property. In any metric space whatsoever, any convergent sequence is Cauchy. The vice versa, so in any metric space, Cauchy sequences may fail to be convergent, but when that fails, you say that that metric space is not complete, right? So when something fails, you say that's a property actually. And it turns out that, for instance, the set of continuous functions with the C0 metric 2 is complete and so on. Okay, so that's all I wanted to say about this. And if you take a more advanced class in analysis, you're going to spend a lot of time with these kind of things, quite possibly. Okay, so now I would like to discuss the mother of all comparison tests for series of numbers, which is a comparison test. And we're going to be using this property of Cauchy if and only if convergent for sequences of real numbers. And I should mention that in this literature, a lot of the theorems are dubbed as tests. There's like ratio test, root test that we're going to look into later, maybe tomorrow. There are things like alternating series tests, Abel test, or Dirichlet test, and there's a bunch of tests. Mostly because these things are supposed to be sort of like practical things. Somehow people sort of like came up with certain series within a certain calculation, and they needed the convergence of that thing. And they realized, oh, maybe I can come up with something that sort of guarantees convergence. So, theorem, comparison test. I'm going to take two sequences, X bullet and B bullet, of real numbers. Let's say that X bullet is big O of B bullet. if x sub n is big O as n goes to infinity of b bullets. I'm going to remind you what this means in a second. And the series with Bn converges then three items. First of all, the series with x sub n as the generic term converges. And so does the series with the generic term x sub n in absolute value. We're going to see an example of why these two are different things later. Why it's good to consider both of them separately. And finally, the value of this infinite sum in absolute value is dominated by the value of this. Okay, now let's remind ourselves what this big O meant. Little o was about the ratio decaying to 0. But I'm saying big O here. In the case of big O, that means that this term bounds this guy. Okay? Typically, people don't write this limit symbol because it's often sort of clear from the context. Here you're taking n to infinity, of course. So that means that asymptotically, as you take n to infinity, b sub n bounds x sub n up to some constant. That's how you read it. There's an n, and there's a c, positive number. Maybe I should write it the other way around, actually. Makes more sense, I think. So if you wait long enough, x sub n in absolute value is bounded by b sub n up to this uniform constant c. Okay? So for instance, sine of n would be O of 1 because it's a bounded function. Okay? And why is this called the comparison theorem or comparison test? Because this says that if you have something like this, such that the sum of these terms add up to some, let's say, finite thing, then certainly the sum of these should add up to some finite thing also. Okay, that's why it's comparison. And often what you're trying to do is you're trying to figure out if this guy converges, which says, so this comparison theorem suggests that if you can find the ends such that this converges, then the original thing also converges. That's the idea. Now, I'm going to do this, 2, and then I'm going to leave to you to verify 1, because 1 follows from 2. If you want, I can choose, once I verify 2, I can choose as b sub n, x sub n in absolute value, and apply the theorem again to get this one. And I'm going to leave this bound to you also. Okay. So the proof of 2. Okay. If this sequence converges, or sorry, if this series converges, by definition that means that the sequence of partial sums for this series converges. So n goes to, let me write, this is a sequence, this is a sequence of partial sums, converges. And maybe, let me denote this by S bullet. But then this is a sequence of real numbers that converges by the thing that we just proved. That means that this is Cauchy. So the finite tails are within an epsilon. But then if this is the case, then certainly I can do the same thing with x sub n's. So x sub k, where k goes from 0 to n in absolute value, is bounded by c times what was it? B sub k. But this can be made to be within an epsilon. Maybe I should write n to n plus p here. So that, let's say t bullet, defined as the partial sums of x sub n, is Cauchy, maybe rather the absolute values, which means that it has to converge, again by the theorem. Which means that the series converges. That's the proof. Now there's perhaps one gap here, namely that here I'm assuming big O. I'm not necessarily assuming that starting at time n, whatever this n was, coming from this Cauchy property, I can do this. But let me leave it to you as an exercise that I can basically re-index everything so that this starts, this works, this argument works for whatever time I need. So let me just say here, exercise, this really works without loss of generality. Okay. Any questions about this? Now, okay, I'm out of time. Tomorrow we're going to study series for which this converges but this doesn't. Okay, that's going to be important. Thank you. I'll see you tomorrow. Good morning. So today we're going to keep working on series of numbers. I would like to discuss some comparison tests. I'm going to give you a bunch of exercises. And then I would like to discuss this Riemann Rearrangement Theorem. This is one of these things that I decided to cut out. So we're not going to prove it, but at the very least I want to talk about the statement. So let's start with this exercise. Yesterday, the last thing we did was this comparison test, which said the following. Under these assumptions, I have two sequences of real numbers, x bullet and b bullet. And b bullet is non-negative. And if x sub n is O of big O of b sub n, which means that asymptotically b sub n dominates in absolute value x sub n, then we said that if, so let me remind you, if this converges, then xn's in absolute value converges. And then from this, we deduce that, or I left it as an exercise, that xn without the absolute values converges. And finally, we had that the limit in absolute value is dominated by this, which is reasonable to expect, I hope, at this stage, because this infinite sum is sort of like a discrete integral, and the absolute value of the integral should be dominated by the integral of the absolute value. This is an expected thing. Okay, and the converse of this comparison test is, as you see, it doesn't start with if this diverges, then this diverges, then this diverges. Okay, the statement, the other way around, is that if xn in absolute value, the sum of them, diverges, then bn diverges. Because it turns out that it might be the case that you have a series like this that converges such that this diverges, in which case you cannot really apply this. And so here's the example. Hang on a minute. Maybe what I said is wrong, actually. So if I have something like this, if this diverges, that's okay too, actually. So you can start without the absolute values here, but certainly this is also correct. In any event, here's a nice example. I'm looking at this formal sum. Minus 1 to the n divided by n. So this is almost like the harmonic series that we had discussed, but with the harmonic series, we didn't have this factor of minus 1 to the n. So now you have the terms alternating, so to speak. And so if I were to put x sub n the terms that I'm adding up, or maybe it's better to call x sub n equals 1 over n, then so this in absolute value, if I were to look into this, this would be nothing but this, 1 over n, and we know that this diverges. But the claim is that if you put this minus 1 to the n, now this sum converges. So it might be the case that some series converges, but when you put absolute values, now it diverges. And so here's the main idea. So what does it mean for this thing to converge? So that's my claim. This series converges. Okay, so I need to look at the sequence of partial sums as usual, right? This is a standard operating procedure. So S sub n is going to be the sum from 1 to n, let's say, of minus 1 to the k times x sub k. Okay? And so let's write this down. A couple of these. So this starts with, so n equals 1 means minus 1 times 1, which is minus 1. Then I'm going to have plus 1/2, minus 1/3, plus 1 over 4, minus 1 over 5 plus or minus goes on like this, all the way up to whatever the sign of, whatever the parity of n is. I need to put plus or minus, but eventually it's going to end at 1 over n. Now the idea is the following. When you try to see what is happening here, so you start at 0, let's say. And imagine sort of trying to sort of see how this S sub n changes. Now first, you're going to jump to the left by a big amount. In this case, it's 1. But really, it doesn't matter, okay? You jump to the left. But then you're going to jump to the right by a smaller amount, which means that, so this is going to be minus 1 here. And if I were to look all the way up to here, that will be minus 1/2. So you're going to jump to the right, but not the same amount. So you're going to jump somewhere here. And then you're going to jump again to the left. But you're not going to go as far as you went in the first place. You're going to undershoot. And then you're going to undershoot again. Okay? And eventually this is going to converge. The point here is that, of course, if you try to make this formal, I'm not going to do the formal argument. What you want to do is you want to look at n even and n odd. Okay? So I'm going to leave that to you as an exercise. So formalize the proof of the claim of the example, namely, so if I were to look at, for instance, S sub 2m, so n an even number, right? What I want to do is I want to, so this is 1, 2, for instance. This is S sub 2, this is S sub 4, and so on. So I want to collect these terms like this, like so, and then maybe plus minus 1 over 3, plus 1 over 4, and then plus minus 1 over 5, plus 1 over 6. And then finally, I'm going to have here 1 over 2 to the m. Here's a plus, minus 1 over 2 to the m minus 1. The point of doing this, of course, is that each of these collected terms I know are negative, or non-positive at the very least. In this case, they are negative, of course, because this is greater than this, so this is a negative number. So is this, so is this, so is this. And this is S sub 2, this is S sub 4, and so on. Which means that if I just look at even indices, the partial sums are going to decrease. And if I were to look at the odd indices, the partial sums are going to increase. So really, what really happens is this. And here you have, maybe I should write it like this, S sub 2 to the p minus 1 here. So in fact, any partial sum with odd time is going to be less than any partial sum with even time. So S sub 2q. Then by one of the many convergence theorems that we know, if this strictly increases and this guy strictly increases, in fact, they have to converge to the same thing. And that value is going to be where the series converges. Okay, so this is sort of toward formalization of this idea. And in fact, when you really think about it, I'm not really using anything about x sub n being 1 over n. And this leads to what is called the alternating series test. And that's going to be an exercise also. But you just use the same idea. it says that if I have, it has a couple different statements I could state, but I'm going to stick to the one that I think that was given in the textbook. Exercise, alternating series test. Alternating. Okay. It says that if I have a sequence of non-negative numbers that is non-decreasing, then the alternating series converges if and only if the limit is equal to 0, limit of the sequence. So minus 1 to the n times x sub n converges. If and only if limit as n goes to infinity of x sub n equals 0. And if you want, this is true as well. Okay? So you see, one side, in a sense, so if a series converges, then the terms has to decay to 0, but not the other way around, right? 1 over n was an example for this. But if you're looking at alternating series like this, then it is true indeed. And the proof is exactly the same proof as this. It's just that you don't use the specific values. Any questions? Yeah.
For a formalization of that proof, you could do some kind of J-key nested interval property statement.
You can do that too, yeah. Yeah, you can look at intervals whose endpoints are these partial sums, and you can look at the.
They're all nested in each other.
You can do that. You can do monotone convergence theorem, whatever. We have many tools to handle this at this point. Yeah.
Well, we should get used to using the series tools that are built for series.
Well, I mean, in this case, I think just looking at the sequence of partial sums just does the job.
Yeah, that's fair.
Yeah. Any other questions? Okay, I am legally obliged to state this. Limit laws hold. I'm not even going to write them formally. I'm going to leave them to you. At this point, I hope you can guess what the limit laws for series should be. Right? The sum of the series, blah, blah, blah. After all, convergence of series is all about convergence of partial sums as sequences, and we know limit laws for sequences. You've spent quite a bit of time in a previous problem set. So here's another exercise that is similar to this fundamental theorem of calculus. It's the so-called telescoping series test. We spent quite a bit of time with this discrete fundamental theorem of calculus. It's very similar. It says the following. So, if I have any sequence of numbers that converges to something, then this guy converges to what? X sub infinity minus x sub 0. Of course, the point of this is that typically you're not given that you have something like this. This is, remember, something like the discrete derivative of the sequence x sub n, but you're given y sub n. If you can realize, it says, that y sub n can be written as the difference of this minus this for some other sequence, then you can just take the limit of the sequence that you split this. Right? So if you can get the antiderivative, you can just evaluate. This is basically the fundamental theorem of calculus, as you see. Very similar to the fundamental theorem. So analogous. Of course, the difference is that this is for so-called improper integrals, not for proper integrals. Okay. I'm going to leave that. So now, here's a new definition. It might be the case, like we saw, with minus 1 to the n divided by n, that a certain series converges, but not necessarily the series whose generic term is the absolute value of the original series. And so that's why we have this phrase, absolute convergence. A formal series, let me say. Of real numbers is said to converge absolutely if this guy converges. If, on the other hand, the original series converges, but not this absolute series, then that is called conditionally convergent. Now, that is not sort of like a commonly accepted term, as I understand. In the textbook, that's how they define it. But for some people, conditional convergence is the same thing as convergence. For instance, for turnstile. But let me just stick to the textbook. But not absolutely. Okay. I think this is not the correct way of defining this, but whatever. Just following the textbook. Then the series is said to be conditionally convergent. So the example you should keep in mind is geometric series is absolutely, hence regularly converges, whereas minus 1 to the n times 1 over n converges, but not absolutely. In other words, it converges conditionally. So alpha to the n for alpha less than 1 in absolute value converges absolutely hence converges, because absolute convergence implies convergence because of the comparison theorem, and hence converges. On the other hand, this guy converges, but not absolutely. In other words, it converges conditionally. Okay, these are the two main examples. Okay. Any questions about any of this? I'm debating if I should do some examples with applications of the comparison test, but yeah. I'm just going to leave them to you to read. I feel like I'm going to mess up the calculations and stuff. Okay, so now that we realize there's a discrepancy here, conditional convergence and absolute convergence, we can discuss this very interesting theorem, which, as I understand, was proved by Riemann. And this has to do with, well, reordering terms in a series to perhaps make it easier to calculate things, right? So, for instance, in this, when I was looking at this example, I sort of collected terms in a certain way. You can also think about sort of reordering terms so that it becomes easier to calculate. But certainly, and let me also say this too, if you had a finite sum, of course, you could reorder the terms you're adding in however way you want, and the sum would end up being the same no matter what you do. But it turns out that if you have an infinite sum that happens to converge but not absolutely, then reordering terms might mess things up, okay? So let me give this definition. This was actually in the first section of the textbook, but at the time we didn't need this definition. For, let's say, x a set, a bijection is going to be just a function from x to itself that has a functional inverse. Bijection is from x to itself of x, let's say, is a function beta from x to itself that has a functional inverse. So beta inverse exists. And I'm going to denote by bij of x the set of all bijections. Of x. If x were a finite set, this would be called a permutation. You just reorder things. Or if you have a bunch of cards, you just shuffle them. And so now I can state Riemann's theorem. In more modern textbooks, this is called Riemann Rearrangement Theorem, but in older textbooks, in one of the textbooks that I saw, it's called the Riemann Derangement Theorem. So, and I think that is more apt, so I'm going to use that. Derangement Theorem. It says this. Let x bullet be a sequence of real numbers. Then there are two situations. If the series with a generic term x sub n converges absolutely, then no matter how you reorder your terms using a bijection of the indexing set, you're going to get the same value. And in fact, this is if and only if. So that's the first step. Converges absolutely. Maybe I should just say, if x sub n in absolute values converges, and in fact, let me write it like this. This guy converges if and only if for any bijection of non-negative integers, indexing set, x sub beta of n. Now I've reordered the terms, and I'm again adding these up. This guy converges, and in fact to the same value. So this limit doesn't change if you have absolute convergence. For instance, in this case, it doesn't matter how you order the exponents. It's always going to lead to 1 over 1 minus alpha, as we saw. However, if your series is conditionally convergent, then in fact, by reordering your terms in a particular way, you can get whatever value you want in the limits. That's why it is called derangement. But doesn't, then for any target value that is possibly positive infinity or negative infinity, there is a bijection, there's a reordering of the indexes such that this converges to that limit. Okay. Now this is surprising, and it just goes to show you that when infinitely many things are involved, you have to be careful. Under certain circumstances, you can just pretend that things are like finitary math, but you have to be careful with things. So maybe I can give you an example. Right? So for instance, I'm not going to prove this, but at the very least, assuming this is true, I should be able to start with these guys, and I should be able to reorder them in such a way that I can just get a sum that converges to some other value instead of this value it converges to originally. And I should mention, at this point, I hope we have the intuition that certainly this is not a nice thing to do, reordering the terms, because sequences are temporal objects, right? They are dynamical objects. And so if you were to change the order in which things appear, certainly the summary, which should be a limit after all, this is sort of like a summary, the summary should change. Or it's not reasonable to expect that the summary doesn't change. The special thing is this, of course. And so let's consider this. This converges to some value between -1 and 0, because it bounces between 0 and -1, and ultimately it stabilizes somewhere, right? You start at 0, then you jump to -1, and then this, blah, 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 blah. So it is this number, S infinity, which is this limit. Now here's the thing. In order to get some other value, let's say 0. Let's say that I'm trying to reorder the terms, -1 to the n divided by n, in such a way that the sum converges to 0 instead of this value, which I know is a negative value. Well, in order for this to happen, I have to be shuffling infinitely many terms somehow. Because if I were to shuffle finitely many terms, I could just excise that finite part, and that would sort of give the same infinite sum after all. Say we want a shuffle beta such that this sum, so in this, now I'm using the shuffled ordering, goes to 0. Well, the point is this. Let me draw this again. In the original ordering, this is what happens, right? So first you go to -1, then to -1/2, then you go a little bit this way, and then this way, and then this way, and then this way. But if I were to reorder, what I could do is, well, instead of using -1 first, I could use some of these positive terms, some of these even terms, so that I have some leeway to the right. I'm not going to write this explicitly. The proof of this basically involves the proof of this part basically involves, given the limit target, explicitly constructing this guy. And the way you do this is you do sort of over under. Because you know that some of your terms sort of increase the sum and some of your terms decrease the sum. So what you can do is you can use positive terms, however many you need, so that you're overshooting, and then you switch over to using negative terms so that you sort of take it down. So we order time so that this happens. Again, my sum starts at 0. I want to end at 0 again. Instead of starting at -1, or going with -1, I'm going to use, let's say, one positive term. The first positive term is going to lead me to 1/2. Then maybe I want to go to -1. So this is the 1/2 term. This is -1 term. So now I'm at -1/2. Then I can use 1 over 4, 1/6, whatever, so that I overshoot. Then I use the next odd term. Then I use, again, even terms. It's going to take longer and longer, you see, because the terms are decreasing after all, in this case. And that's basically the idea. Writing it down is sort of technical and it's not very illuminating. And as far as I'm concerned, this is not used, it doesn't have major applications. It's still good to know, of course. So maybe I should just summarize. Use even times to overshoot the target limit. Then use odd times to make your estimate better, basically. That's the main idea. Any questions? I didn't know this, but there's a whole cottage industry about reordering things. Of course, not with numbers, but let's say your series has terms in a more complicated vector space, a space where you can add things. And you can take the limit too. Maybe this is what is called the normed space. And so given a series, what type of limits can you get? This seems like a very rather interesting sort of question, but I don't really see sort of the sort of broader value of it. I've just learned about it yesterday, I think. But there's a bunch of papers and books and all that stuff. Okay, any questions about this? Okay. Now we have about 10 minutes. There are two tests that I would like to discuss at the very least. These are very useful tests. One of them is called the ratio test. The other one is called the root test. It basically says something about the convergence of a series like this, where these guys are non-negative. Root test says that, okay, so if you want to figure out the convergence of this, look at this expression. In one of the first problem sets, actually, you sort of looked at sequences of this form, and somehow where this converges to, or if it doesn't converge, its limsup tells you something about whether or not this converges. So it's going to take longer to prove these, so I'm not going to start them. So I'm going to just give some definitions that we're going to need later. And then the ratio test, which you saw in the same problems, says again something about the convergence of this based on the asymptotic behavior of the sequence of ratios. So these are very important things. We're going to discuss these and prove these properly, probably tomorrow. But for now, let me just give some definitions, because ultimately we need to at least talk a little bit about series whose terms are functions. Okay. Okay. Yeah. So let's just do this. Let what do I want? X be a metric space. Okay. And F bullet be a sequence of functions on X taking real values. Then, of course, I can look at the power series, or rather the infinite series, whose terms are these functions. Then the formal series of functions is said to converge pointwise or uniformly, right? We have two different flavors at the very least for function convergence. Same thing holds for a series of functions. Now, if I feed an input to each of these functions, now f sub n of x is a number. So now this is nothing but a series, formal series of real numbers. I'm saying that the series of functions converges pointwise if this series converges for any x. And otherwise, if this converges uniformly, let me write it here. Is said to converge uniformly. How can I define uniform convergence for a formal series of functions? What do you think?
If your sequence of sums converges uniformly.
Right, so I can just look at the partial sums as usual. Well, sum of functions is a function, so I have a sequence of functions, and I'm asking that sequence of functions to converge uniformly. If, let's say, S sub n converges uniformly, where S sub n is the sum of all functions from 0 to n. This finite sum certainly is in this set of functions. Okay. Let me ask you then, if I have a series, formal series of continuous functions that happens to converge uniformly, can I say that the limit function 2 is continuous? let me call this S sub infinity. Then S sub infinity 2 is in continuous functions. I have infinitely many continuous functions. I add them up, and I'm saying that somehow this infinite sum converges, uniformly converges. Is it the case that this guy, the limit function, 2 is continuous? Any guesses?
Feels like it should be true, but you can also do like the, say, you can do the Fourier thing of decomposing a discontinuous function into a whole big pile of sine waves. That might constitute a counterexample.
Well, yes, but that doesn't converge uniformly. It converges in a different sense. It converges in L2, let's say, which we didn't discuss. But what you can say is that this is, by definition, the uniform limit of the sequence of continuous functions. Because I have finitely many, if I have finitely many continuous functions, certainly the sum of them, 2, is going to be continuous. And we know that the uniform limit of a sequence of continuous functions is continuous. So the answer is yes. Okay. And that will be it for today. We're going to continue tomorrow. Thank you. Okay, let's start. Good morning. So we're going to talk about these important tests, 3 of them, for convergence of a certain series of numbers. Remember, yesterday we had finished with some definitions of related series of functions. So we're going back to this because I want to spend some time. And then I thought it would be a good idea to discuss some of the examples given in the textbook. Initially, I thought I was just going to skip these calculations, the problem of determining whether a certain series converges. But I feel like the arguments given in the textbook are not as sort of clear, so I want to sort of discuss these as well, and then we'll be on our way. Are there any questions before we start? So I'm going to be taking attendance today. Here's the sheet. And so the first test, this was actually something that we used already, but let's make it more formal. I should mention, we had discussed this comparison test, right? And I told you that the comparison test is the mother of all tests when it comes to convergence tests for series. And indeed, this test and then the root and ratio tests that we're going to discuss today also, they all are, in a sense, corollaries of the comparison test. And we had used this integral test when we were looking at the zeta function. Remember that the zeta function was this formal series. I had this S as a parameter, and zeta of S was the sum of the reciprocals of integers raised to the power S. It's kind of bizarre to think of this thing, but somehow this turns out to be important. And we said that this is convergent if and only if S is a number that is positive, this is greater than 1. Converges. That's what we said. Now for the convergence part, for instance, zeta of 2 I had done in class. So the reciprocals of the squares of integers, that converges. And the way I argued about that was that I compared this sum to the integral of 1 over x squared. So I was really using this. But for the divergence of zeta of 1, we used a different argument that also has sort of like a general sort of framework. It's called Cauchy condensation test nowadays, but maybe in the next problem set you're going to see problems about that. But this integral test is really telling you that, in fact, I could have used, again, an integral to figure out that zeta of 1 diverges also. Instead of comparing to 1 over n squared, I would be comparing it to 1 over x to the s, or 1 over x. So the idea is to figure out whether or not this converges or diverges, compare the sum to 1 to infinity 1 over x to the s dx. The point of doing this, of course, is that I can integrate this. It's relatively easy to find antiderivatives and so on. Okay, so here's a proof. Maybe I should write it here. Oh, let me write it here. And maybe let me add one more hypothesis to make it slightly nicer, this statement. Oh, did we all sign this? Okay. Let's also assume that f is non-increasing. Also assume, so here, I actually don't need this, but okay. That's how this was given in the textbook. Let's just follow the textbook. The idea is this. Let me start with this part. Now this is an improper integral. That's why there is the word converges there. Yeah. And so by definition, recall that whenever, so this exists if and only if the limit as rho goes to infinity of the definite integral from 1 to rho of f exists, and this limit is this improper integral. Now, this variable rho is a continuous variable. And we had discussed how in virtually all situations where we're interested in taking these limits, instead of taking this limit over this continuous parameter, I can take a limit over a discrete parameter. Okay, so I can take n to infinity, where n is an integer. So maybe I should write this 1 to n, like so. But then by the additivity property of Riemann integrals, I can write this integral from 1 to n as the sum of the integrals from 1 to 2, 2 to 3, 3 to 4, all the way up to n minus 1 to n. So maybe I should keep writing it like this. So it's over here. So I want to go from k to k plus 1. I want to integrate. And then what should be the bounds. So I should start at k equals 1, and then I should end at n, which means that k has to be at most n minus 1, I think. Yes. It's not going to matter too much. But you see, for any integer k, this definite integral is a number, because I'm assuming that f is locally integrable. So this is a number, so this is a finite sum. And I'm taking the limit of one of the endpoints of one of the bounds of the finite sum, which means that this indefinite integral, or rather, this improper integral, I can think of as a series in and of itself, series of numbers. Okay? Like this. Sorry about the lines. And so now I have yet another series that I derived from this. It's a formal series, of course, because at this stage I don't know if this improper integral converges. But the convergence of this is equivalent to the convergence of this series. Okay? But now I can use the comparison theorem, comparison test. And so let me continue here. And so this is the typical picture. So we start at 1, and then somewhere here is n and n plus 1. Okay? And I assumed that f is non-increasing. So if the value of f at n is this height, then at n plus 1 it's somewhere here perhaps. So the function, it might have discontinuities and stuff like that, but that's not really that important. Okay? But also I'm assuming that this function f interpolates the sequence. So this height is on the one hand f of n, but on the other hand x sub n. And this is x sub n plus 1. And of course, the Riemann integral of f, in other words, one of these terms, is bounded from below and above by x sub n's, right? Because the Riemann integral of f from n to n plus 1 should be bounded from below by the area of this. The area of this is nothing but the number x sub n plus 1. And likewise, it should be bounded from above by the area of this rectangle, which is area x sub n. So the integral of f from n to n plus 1 is greater than x sub n plus 1 and less than x sub n. This means that on the one hand, you see the series, this series, which is the improper integral, whose generic term is this integral, is bounded by this guy. So this is O of x sub n, but on the other hand, at the same time, this is O of this. Well, maybe let me write it like this. Okay. And so once we have this, I can now refer to the comparison test, which says that because of this, if the series with x sub n converges, then this series with this converges, which means that the improper integral converges. And on the other hand, if the improper integral converges, that means that the series with this as a typical term converges. Again, by the comparison test, the series with typical term x sub n converges also. So the convergence of this series and this integral are equivalent. And that's the end of the proof. Okay. And it turns out that, so you can look at the discrepancy between these two terms and these two terms and look at the limit of that discrepancy. And that discrepancy, that limit, gives you a certain quantity. And it turns out to be an important quantity. Shows up in a bunch of different places. And in the next problem set, you might see problems about that. Okay. Now, as you see, it's fairly intuitive as far as I'm concerned. It's expected. Any questions? Okay. So now let's talk about the root and ratio tests. First, I'm going to write them down. Then I'm going to describe some examples. See if we can sort of figure out if they converge and diverge. And then in the remaining time, I would like to discuss at least elements of the proof of root and ratio tests. They're not too complicated, but still. I feel like it would be a good reminder of some of these terms, some of these ideas, because they involve these phrases, limsup and liminf, that we had discussed basically 2 months ago. And I'm going to write both of them on this board. And on the other board, I'm going to write examples. So you see, integral test is a corollary. It follows from the comparison test. Root and ratio tests, too, are going to be corollaries of the comparison test. Okay. Root test. Let x bullet be a sequence of real numbers, not necessarily non-negative. Then I want to deduce something about the infinite series whose generic term is x sub n using the fate of the sequence of roots. And in older texts, instead of root, they use the word radical. It seems now root is more common. It has 3 parts. If limsup as n goes to infinity of xn in absolute value to the power 1 over n, probably I should be writing these smaller, but okay. If this limsup is less than 1, then the series converges absolutely. Let me just write it like this. And absolute convergence, remember, implies regular convergence. If, on the other hand, the limsup of the same sequence is greater than 1, then the series diverges. I'm going to remind you in a second what this limsup was. But if you don't remember, just pretend that it's just limit. The point of writing it like this is that limit of the sequence need not exist necessarily, but the limsup always exists. And that's why it is important to look at this. If this limsup is greater than 1, then the series diverges. So it cannot converge. And if the limsup turns out to be equal to 1, the test is inconclusive. It might be the case that the series diverges or converges. Inconclusive. Both can happen. Okay, that's the root test. Ratio test, instead of looking at the sequence of roots associated to this original sequence, looks at the sequence of the ratios of the consecutive terms. Of course, this is not the first time you're seeing this, because in problem set 1 or 2, you've handled problems about these two things ultimately. Maybe not series, but at least sequences of this form, right? Ratio test. Now, because I'm going to look at the ratio of consecutive terms, I want my sequence to never be 0 for simplicity. So let expolate be a sequence of non-zero numbers. Then again, I'm going to look at limsup, but this time I'm going to look at liminf as well. And a similar thing happens. Then, if the limsup as n goes to infinity of x sub n plus 1 in absolute value divided by x sub n in absolute value is less than 1, then again the series converges absolutely. For some reason, Taylor states the root test using limsup, but not ratio test. For some reason, he assumes that these limits exist. You don't need to. Then x sub n in absolute value, the series of these converges if the liminf of the same thing is greater than 1. Then the original series converges, diverges. And finally, if in any other cases, maybe if limsup is equal to 1 or liminf is equal to 1, whatever, otherwise the test is inconclusive. Okay. Now, we're going to prove these toward the end of the class. Let me first transition to examples. But let me just say that both of these are corollaries, like I said, of the comparison test. And you're comparing, in either situation, the series you're trying to figure out to some geometric series. Okay? So powers of one number. But first, let's look at examples. These are from the textbook. Okay. So here are some formal series. Let me first write them down. N divided by 2 to the n. One over n factorial, for instance. What else? N divided by minus 2 to the n. Then I have n divided by n squared plus 1. Then I have 3 root n divided by 2n squared minus 1. And let's say that this last one starts at 75. Now, these are formal series, okay? And the question, there are two questions, but we're just interested in the first one. So the two questions are, whenever you see a formal series, does it converge? And the second question is, what is the limit? Right? The first question is, of course, it is necessary for the second part to make sense. But sometimes you just need that a certain infinite series doesn't blow up. And you don't really care about what the specific value is. Now, for more quantitative purposes, you might be interested in the specific value. But these are two different concerns. Okay? And if you had a series of functions, you would be looking into in which sense the series converges also. Is it pointwise, uniform, some other sense, blah, blah, blah. But for numbers, there's only one sense, or maybe two. Converges or absolutely converges. So any guesses? Let's start with the first one. Does it converge or does it diverge? What do you think? Now, if you didn't have this numerator, n, it would converge. That would be the geometric series. Okay? But now, you see, the numerator, even though the denominator decays, the numerator increases. Any guesses?
I'd say it probably converges.
Why do you say that?
I mean, like from a very heuristic sense, the bottom function grows way faster than the top function.
Well, that's true.
Which is like not a particularly helpful notion for being rigorous, but like if we're less rigorous, then we could explain it with that.
Okay, let's start with this then. I'm going to look at the reciprocal of this. What your colleague is suggesting is that, at the very least, in order for a series to converge, we had this exercise, I had left it to you, the terms have to decay to 0. And certainly, by L'Hopital whatever, I can see here that this term doesn't decay to 0 because exponentials grow faster than linears. Okay? So the term, generic term, doesn't decay to 0, so that means that this cannot converge. So this diverges. Okay, maybe I should write because 2 to the n divided by n goes to infinity. So the generic term decaying to 0 is a necessary condition for the convergence of the series. But it's not sufficient because 1 over n, remember, this also decays to 0, but this doesn't converge. So it's not sufficient. What you're saying is correct, of course. Somehow the heuristic is that not only does this decay to 0, but it decays so fast that ultimately this should converge. And the way to formalize this idea is to use the comparison test. So the idea is this. Let me just give you some heuristics. Okay, I start at 1. That's 1. How does 1 over 2 to the x or 1 over 2 to the n look? It's an exponential decaying thing, and it starts, so it's at 1 here, right? And something like this. This is 1 over 2 to the x, let's say. Now, if I were to multiply this by x, that means that I am, as n goes to infinity or x goes to infinity, I am amplifying the signal by a linear term. Right? Because instead of this decaying like this, you have this y equals x, and you sort of like, maybe it would be nice to sort of see this on Desmos. The moment you multiply this by this, you're sort of amplifying this decaying term in a way that this sort of becomes sort of like this. It's hard to draw. But, put it on Desmos and you can see, you're going to be able to see it. But the idea is that perhaps if I were to lower this 1 over 2, maybe I should write this like this. If I were to make this base, base smaller, this exponential function would decay even faster, right? And I guess it doesn't, there's an asymptote here. Is there an asymptote? No, there is no asymptote. I was right. So for instance, if I were to look at 1 over 3 to the x, it would decay faster than 1 over 2 to the x. Again, at 1, it would be 1. It would be like this. So this would be 1 over 3 to the x. And maybe 1 over 4 to the x would be even more dramatic and so on. The strategy then is going to be to find some value. Oh, it should be the other way around, of course. Because this decays slower. Let's write 1 over 1.9. Okay. Right. And so the strategy is going to be to compare this term to some exponential function that I know decays faster. Okay. Then, if I can do that, if I can find this value, then comparison test is going to be sufficient. So, okay, let me erase this. So for this guy, what I want is this. I want this to be O of some exponential term. And it has to be faster, it has to decay faster than 1 over 2. So it's going to be of the form 1 over 2 minus epsilon to the n for some small epsilon. If I can do this, then I'm done. And so what does this mean? This means that I need to find some constant c and sufficiently large n such that this happens. Okay, now send this to the other side. So this is 2 divided by 2 minus epsilon to the n. But of course, epsilon is supposed to be a positive number. So 2 is greater than 2 minus epsilon, which means that this thing is some number that is greater than 1. And then by L'Hopital, whatever, I know that any exponential function grows faster than a linear function, which means that for sufficiently large n, this is going to be true for some constant. C is not important, okay? So that means that for sufficiently small epsilon, I can curve this by this guy, and I know that this converges. By the comparison test, that has to converge as well. Okay, this is the heuristic. So this big O is a way to be vague, but in a very formal manner. And ultimately, all this business really tells you that if you're trying to figure out the convergence of this guy, you could say, oh, this guy is linear, this guy is exponential, so the convergence of this, so for the convergence question, I can just pretend that this doesn't exist. And this is basically a geometric series, so it converges. Okay? Any questions about this? Now, I'm not saying anything about the limit itself, okay? If you start doing these, of course, you can keep track of your estimates and stuff like that and still get some estimate, but you would have to be more careful. So you can use big O formalism to sort of just eyeball whether or not certain things converge. But if you want to be more specific about the limiting values, this is more of an applied question, of course, then you have to be more careful. Questions about this? Okay, how about the second one? 1 over n factorial. Of course, this converges to E, but let's say that this is the first time you saw this. How could you argue that this converges or diverges?
With the ratio test, ratio test.
So your colleague is suggesting, look at the ratio of the consecutive terms. So 1 over n plus 1 factorial divided by 1 over, so this factorial is multiply all the numbers from 0 to n. 1 over n factorial, so this is just going to be 1 over n plus 1. This decays to 0, which means that by the ratio test, it converges. You can do it like this. You can just use the comparison theorem by itself and say that, oh, n factorial grows faster than any exponential, right? Because, so, n factorial is n minus 1, n minus 2, dot, 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 1. So this is basically like an exponential function, except that instead of multiplying the same number over and over again, you keep multiplying larger and larger numbers. So this is going to be up to some constant, blah, 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 2 times, 2 times, 2 times, blah, 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 2, n times. For large n factorial is going to be larger than 2 to the n, which means that their reciprocal is going to be the other way around, which means that 1 over n factorial is big O of 2 to the n. 1 over 2 to the n, and I know that the geometric series converges. Again, by the comparison test, I'm done. You can do it that way too. Okay? The point of all this is to be fast. Okay. How about this third one? Any guesses?
I don't want to be carrying the whole class, but this should be possible with the alternating series test.
You can do that, yes. Or you can just look at the, again, comparison test as before, because for comparisons, you're just looking at absolute values anyway. So you can see that this is nothing but minus 1 to the n divided by this guy. And we know that this goes to 0, whenever you have a sequence that converges to 0, if you were to multiply it by -1 to the n, that series is going to converge. Alternating series test was this. This, and these two are pretty much the same idea. Again, by big O considerations, you can pretend that this is basically 1 over n. So, and in fact, you want to write it like this. 1 over n is big O of this guy. Okay, and this diverges, which means that by the comparison test, this has to diverge. And likewise here, I want to think of the numerator as n to the 1/2. The denominator is n squared, which means that this is basically 1 over n to the 1.5. So 3. And once you get the hang of this big O, it's very convenient. This is basically this. What did I say? So 2 minus 1/2 is 1.5. And I know that this converges. So that has to converge. And that's it. Okay. I highly recommend that you sort of go through these again and make sure that you understand these. Actually compute this, that this is big O. Once you start seeing these patterns, it becomes very convenient to be able to just eyeball something. You just pretend that, oh, this is basically 1 over n, okay? So. Okay. Maybe I should leave one more, give one more example. Let's say that this, next one is this. So n, oh, does it matter if that the series starts at 75? It doesn't matter because it's only finitely many terms. You can just excise finitely many terms. And that's also included in the big O notation also, right? So it requires that a certain thing holds after finite time. You can just excise it. So let's say that I have three times this, okay, 2 times n to the 2 plus pi to the e, I don't know. This is like a standard calculus thing. You just generate random things that has no meaning as far as I'm concerned. But the point here is that you get to pretend that this is basically 1 over n to the 2 minus this. So, and this is, 3. So this is 8. 8 minus, or maybe I want to do 6 here. Then this is, that should be an n. So this is 1 over n to the 1/2, which means that this has to diverge. Okay, diverges. Not too deep. Perhaps the fact that you can do these eyeballing things is a deep thing, but not the calculations or approximations themselves. Any questions about these? Okay, so let me first assume root test and show ratio test. Ratio test follows from root test. By way of this problem in a previous problem set that we had discussed, or that I had given to you, that you had spent plenty of time, namely that the limsup and lim-nth of the sequence of roots, they are squeezed within the limsup and lim-nth of the sequence of ratios. from root test. From previous problem sets, we have this. And we also know that the sequence converges if and only if its limsup and limf are equal. Well, I guess we're not going to need that. But the point is that assuming the root test, if the limsup of this ratios, if this is less than 1, then certainly so is this, which means that I can apply the first part of the root test to deduce the first part of the ratio test. For this part, if the lim-inf is less than greater than 1, then that means that lim-sup of the root sequence is also greater than 1, which means that I can apply this to get this. And these there's nothing to prove there. This is sort of like one instance where part of the theorem is stating that there are certain situations where the theorem doesn't work. In general, you just don't state that. But maybe I should ask you, can I think of how can I come up with an example where, let's say, the lim-sup of the roots converges to 1, but maybe the series doesn't converge or converges. So I'm trying to come up with an example to which neither of these apply. It turns out that if you were to look at the zeta function type stuff, this gives you examples. So exercise. So zeta of s, which is, again, n from 1 to infinity, 1 over n to the s. No matter what s is, you're going to realize that both this sequence and this sequence converges to 1. For any s, lim-sup as n goes to infinity of 1 over s to 1 over n is 1, and so is, or limit itself actually, so is the limit of the ratios. So 1 over n plus 1 to the power s divided by 1 over n to the s. But for some values of s, this series converges, for some it doesn't. So that's why these tests don't work if this lim-sup or lim-inf, whatever. If you're getting to 1 in the limit, you cannot use them. And this turns out to be an important idea somehow. Somehow to get to get certain things, you want things to stay away from 1. When things get closer to 1, it's very hard to handle. Okay, this is sort of like a cryptic thing to say, but it is true. Especially in my work, for instance, it shows up all the time. You want certain numbers to stay away from 1 as much as possible. If it's less than 1, it's good. It's greater than 1, it's good. And the farther, it's better. And you don't want it to be closer to 1. Okay. Okay, so we have 2 minutes. Let me then start with the proof of this. So the important part is this, actually. I'm going to leave to you to show that in the second assumption, if the lim-sup of the root sequence is greater than 1, then in fact, x sub n does not converge to 0, which means that it has to diverge. So that's going to be an exercise. So here's the idea. This then xn cannot converge to 0, which means that the series cannot converge. So what you need to show is this. That's part of the exercise. The important part perhaps is 1, and I would like to spend some time on doing this so that we can review this definition of the limsup also. The point is going to be the following. Let's call this number alpha. Alpha is a number less than 1, and it's a positive number also, somewhere here. If alpha is less than 1, as in the assumption for item 1, then if I were to compare x sub n to this series, so let's say alpha plus epsilon, what we're going to show is that x sub n is in fact O of alpha plus epsilon to the n for sufficiently small epsilon. It has to be small enough so that this alpha plus epsilon is between alpha and 1. Then we're going to use the geometric series test, comparison test, and compare it to the geometric series to get the convergence. Okay, that's going to be the proof, but I'm out of time, so we're going to have to do that on Friday. Thank you. Okay, let's start. Good morning. So we're going to discuss this proof of the root test today. Then I will give another test specifically for series of functions. It's called the Weierstrass M-Test, and that'll be it, at least for general purpose sort of infinite series business. Next week we're going to look at analytic functions a little bit and Taylor approximation, and if you have time I want to do something slightly more suspicious, just like we did with generalized or weak derivatives. I would like to talk a little bit about operational calculus or operator calculus, where you sort of pretend that differentiation perhaps is sort of like an independent variable somehow, and you can do sort of algebra without doing any calculus, and it seems to work somehow. Okay. Are there any questions? Okay. Yeah, don't worry too much about these kind of things. Ultimately, as you can see, I am fairly relaxed at this point because we've covered the main sort of like punchline of this class, fundamental theorem of calculus. Anything else, especially like the things that you cover in the last weeks, it's hard to expect that they're going to be sort of significant or they're going to stay in your mind. What is more important, of course, is the fundamental theorem, but still, these are important things, and depending on your psychological makeup and predilections and stuff, you might end up using these more than the other stuff that we studied earlier in the semester. I should mention that the next problem set is up also. It's nice. I like the problems. Okay, so the root test is this. I have a sequence of real numbers, and I'm looking at this quantity, limsup of the sequence of roots. Of course, for this to make sense, I have to make sure that the thing I'm taking the root of is non-negative. That's why I'm putting the absolute values there. And another word for root was radical, of course. And then I look at this limsup, and it had a couple of statements. One of them was if the limsup is larger than 1, something happens, namely that this series diverges. If you remember, on Wednesday, I had left it to you to verify that. But the verification is pretty much the same thing. And as we're proving this, you're going to see how You might sort of verify the divergence part of the root test as well. In any event, so it says that if the limsup of the root sequence is less than 1, then this formal sum converges absolutely. And I told you that underneath the hood, this is nothing but comparison to some geometric series that converges. Okay, so what I would like to do is take it slow, because even though we defined this object, limsup, 2 months ago, 3 months ago, we didn't spend too much time on it. So I want to sort of slow down and see how we can use this. So do any of you remember the definition of this limsup? Okay, so whenever you see something like this, another notation that is very common for this is lim with an upper bar. It's the same thing. Some people don't like writing limsup. And if you want to denote lim inf, you just put an underbar. So whenever you see something like this, it's a minimax, okay? So you're trying to capture this asymptotic behavior of the sequence, and you're going to have to do some minimax over times. And you're going to have to, so the point is, because you're trying to capture asymptotic behavior, somehow, systematically, you need to get rid of the first n terms and see the asymptote, see what happens in the asymptote. And so, in this case, limsup is inf sup, okay? First you figure that out. So the way I think I remember this is that this stays this way, and then lim in fact is an inf. Okay, that's how I remember it. So lim sup is an inf sup, so minimax. And if I had lim inf, that would be maximin. Lim inf would be sup inf. Okay. Lim sup as n goes to infinity of xn in absolute value raised to the power 1 over n is, by definition, inf over uppercase n, starting at 1, of the sup of lowercase n after uppercase n of this thing. Now somehow this inner term is something like the tail, and you're sort of taking the tail to infinity in a sense. Okay. And the point here is that, so let's parse this. So given any uppercase n, if I were to fix the uppercase n, the set of all those numbers of this form, where lowercase n varies over uppercase n, is a non-empty set of real numbers, possibly unbounded. But in any event, this sup is, it could be infinity, it cannot be negative infinity, but it always exists in this sense. And then over this, now as I vary uppercase n, now I have a set of extended real numbers. Each uppercase n contributes one such extended real number. And then it's non-empty, and then I'm taking the n forward, okay? Which means that this always exists as an extended real number. So that's the benefit of looking at the limsup instead of the lim. Another characterization for the limsup was that we would take the sequence, and we would take any subsequence whatsoever that converges to something, and the maximum limit you can achieve this way is the limsup. That was another characterization. Now, in this case, the terms I'm taking the limsup over are non-negative, which means that this limsup is going to be some quantity here. Okay, let me call that alpha. Now I want to slowly open up the definition and see what I can get. Okay, remember, I'm trying to get some geometric series. In other words, I want something like beta to the n. I want to be able to compare x sub n to this. Beta to the n, and I want beta to be less than 1, of course. If that can happen, if I can do this, because I know that the geometric series converges, this is going to converge absolutely by the comparison test. Okay. Now, let's slowly open this up. I am saying here that alpha, this extended number, is the nth of all of these. Now, let's remember. That means two things happen. First of all, alpha is a lower bound for each such quantity. And furthermore, any number that is larger than alpha cannot be a lower bound. Okay. This is a review, of course. So, for any uppercase n, alpha is a lower bound of this quantity. This just says that alpha is a lower bound, and I need to also say that alpha is the best lower bound. That is to say, and for any epsilon positive, if I were to look at alpha plus epsilon cannot be a lower bound for terms of this form, which means that there's a capital N that possibly depends on epsilon, such that this expression with this specific capital N is less than alpha plus epsilon. For any epsilon, there is an n sub epsilon such that this happens. You see, I've just unpacked this outer inf, and it became these two logical statements. But now I can do the same thing with both of these statements. The first statement says the following: alpha is less than or equal to the sup of this. So if I fix uppercase n and very lowercase n's, at least one of them has to exceed alpha. Okay, that's what this means. And so this means that for any n, there is a lowercase n that is larger than uppercase n, such that alpha is less than or equal to this term. This statement came from unpacking this statement. Okay? I'm saying I have a bunch of numbers, their sup is greater than something, which means that at least one of them has to be greater than that number. Okay? But I need to unpack this as well. For any epsilon, there is an uppercase n that depends on epsilon, such that sup of all of these terms, so you see now the independent variable is lowercase n, is always less than this guy, which means that for any n, for any lowercase n after this uppercase n sub epsilon, this quantity has to be bounded by this. I cannot say anything about the lower bound because it just says that for some n larger than n sub epsilon, this term is greater than or equal to alpha, which we listed here already. So that will be redundant. So I'm just dropping, sort of unpacking this part, and I'm just focusing on this part. Okay? Now, for now, actually, so far, we didn't use anything about alpha being less than 1. And I'm going to keep going like this. Now, first note this. I can package the second statement using big O notation. How can I package it using big O? Well, maybe I can go on. Let me go one step further and put the 1 over n to the other side. Because in both of these, you see, I have x sub n to the 1 over n, but I don't want to see 1 over n because it looks kind of scary. I'm going to send it to the other side by taking the nth powers. And then orders of the inequalities are not going to change. So, for any n, there's an n such that alpha to the n is less than or equal to x to the n, x sub n in absolute value. And for any epsilon, there is an n sub epsilon such that for any n after n sub epsilon, x sub n in absolute value is bounded by alpha plus epsilon to the power n. I just unpacked the definitions. Now, the way to pack this statement using big O is to say for any epsilon, that's one way, for any epsilon, x sub n is big O of this. Okay. Now I can use alpha is less than 1. If I were to choose epsilon small enough so that alpha plus epsilon is less than 1, so let's say for epsilon, so here's alpha, here's 1. I want alpha plus epsilon to be here, which means that I want epsilon to be less than 1 minus alpha. Okay? Whatever this number is. So alpha plus epsilon raised to the power n is a geometric series that converges because the number whose power I'm taking is less than 1. This is going to be less than 1. Hence, by the comparison test, so too must x sub n in absolute value converge, which means that x sub n, the series x sub n, converges absolutely. Okay. Now, in fact, while we're here, let's also do the limsup greater than 1 part. This was the divergence part. It said that if the limsup is greater than 1, then the series diverges. Now we know that if a series converges, its terms has to decay to 0. In the contrapositive direction, that means that if a sequence does not converge to 0, then the infinite sum with those terms have to diverge. So it suffices then to show that if the limsup of the root sequence is greater than 1, then in fact x sub n cannot go to 0. How can I see that? How can I argue for that? With using something that's on the board. This is the other part, you see, that we didn't use. This says that there is some subsequence of x sub n that is bounded from below by alpha. And if alpha is greater than 1, that means that it cannot converge to 0. So it has a divergent subsequence. Convergent sequences don't have any divergent subsequences, right? So I can say capital N, if I were to choose capital N to be 1, then there will be n sub 1 greater than 1, such that the corresponding term is bounded by alpha. But then for capital N, let's say this value, this number, plus 1, then I would have n sub 2 greater than n sub 1, such that again, alpha is a lower bound, and so on. This way, I could construct a subsequence of x bullets that is bounded from below by alpha. Okay. Well, I guess I should be looking at this part. So alpha to the n minus 1, n minus n2, and so on. The point is that when alpha, this limsup, is greater than 1, instead of looking at alpha to the n, I can replace it by 1. Okay. Any questions about this? Here's an exercise. We had discussed how if you were to look at a formal series consisting of continuous functions that happens to converge uniformly, then the limit series 2 is continuous. Similar things happen for integration, for instance. And one of the previous problem sets, in the last problem set before the second midterm, there was a problem, the problem that was graded for accuracy. So what I'm going to write now about infinite series of functions follows immediately from that. But I'm going to leave it to you to formalize. And of course, we also have that the integrals converge to the integral of the limits. So exercise. Let's let I to be a closed and bounded interval. Infinity. And let me let f bullet to be a sequence of Riemann integrable functions. In the textbook, they stated for continuous functions, but you don't need to have this assumption. if the formal series f sub n converges uniformly, in other words, this is a function, right? Then, in fact, this limiting function too is Riemann integrable, and its Riemann integral is the series of the integrals. As you see, this is yet another instance of being able to interchange limits. Instead of first taking the limit that defines the series, then taking the limit that is implicit in Riemann integration, you can do it the other way around. Another way of saying this is that when you have a uniformly convergent series of functions, then to integrate the limit function, you can integrate term by term. That's also one way of saying this. Okay. And all you need to do to figure this out is to say that, oh, so this converging uniformly means that this sequence of partial sums, which are functions in and of themselves, of course, this sequence converges uniformly to some function. But I know that if I were to add up finitely many Riemann integrable functions, the end result is going to be Riemann integrable, which means that S sub n too is Riemann integrable. And you've shown in a previous problem set that uniform limits of Riemann integrable functions is Riemann integrable. And you have this thing. Okay, so it follows immediately from that. Okay, any questions? So let me introduce one definition. We had discussed this C0 metric. There is also something called a C0 norm. That's where instead of looking at the distance, C0 distance between two functions, you're looking at the distance of one function to the function that is constantly 0. It's also called the soup norm and L infinity norm. It has, as usual, a bunch of different names. They erased these boards with something bizarre today. See, it stains. F be a function. Taking real values. We define the C0 norm of F by the following. Norm of F is F in absolute value, But just so that you don't confuse it with the function that is the absolute value of f, you put a subscript there, c0. This is a number, and it's defined to be the c0 distance of f to the function that is constantly 0. In other words, this is nothing but sup of f of x in absolute value as x varies in x. By the way, I keep saying C0 norm and stuff like that, and we had discussed C1 functions, CK functions, and so on. There are likewise CK norms. What you do is, instead of just looking at the function, you also look at f prime, f double prime, and so on. You add all of them up. That gives you, for instance, the C2 norm and stuff. So maybe I should write that. So for instance, C2 distance between two functions that are twice differentiable. So C0 distance, and then C0 distance between their primes, their first derivatives, and the C0 distance between their second primes. In the previous problem set, we were talking about perturbations, two functions being close to each other in C0 distance. That means that the functions themselves, their values are close. But for instance, if two functions are close in the C1 sense, that means that not only are the functions themselves close, but also their slopes are close at the corresponding points. So that's like more restrictive in a sense, gives you more control. Anyway, so this is this. And then the Weierstrass M-Test says something about the uniform convergence of a formal series like this, made up of functions, in terms of the series of the norms. Namely, as here, I'm taking x to be just a set, and I'm going to take a sequence of functions M says that if the series, numerical series consisting of the C0 norms of this function sequence converges, then the function sequence, rather, the function series converges uniformly and absolutely, in fact. Then converges absolutely, uniformly, and absolutely. Just like with series of numbers, you can ask, oh, is this functional series converge absolutely or conditionally and so on, in tandem with whether or not the convergence is pointwise or uniform. So you actually have four different options. In this case, if this converges, the series of norms converges, then the original sequence, the series converges in the best possible sense. And in fact, in the next problem set, you're going to have, in fact, two problems around this test. First of all, the other way around doesn't work in general, but sometimes it does, and you're going to sort of see situations like that. Okay. Maybe I should mention this as well. Why is this called the M-test? Because typically, instead of saying this series converges, traditionally, you would say that the C0 norm of the function f sub n is bounded by m sub n. M is this letter that people decided to use. And if the series of m sub n's converge, then the functional series converges uniformly. That is just like a traditional thing. And in some textbooks, they don't mention this m. In some textbooks, they still use it. In our textbook, they still call it the M-Test. That's why I'm calling it like this, but it's not important. Okay, so the proof of this, let's think about this. Assuming that this numerical series converges, I need to show that this guy, again, this is, I can imagine this to be the sequence of partial sums, and each of these partial sums itself is a sequence, is a function, which means that I'm looking at uniform convergence of a sequence of functions. But I need the limits, okay? And just like we had a problem before about having this target limit, here too we have this problem. Which means that instead of looking at whether or not the sequence of partial sums converge, or rather where it converges to, we want to show that it is Cauchy. After all, the set of all functions on x taking real values is something like a metric space. The only property that is sort of like dubious a little bit is that the distance between two functions could be infinity. So maybe it's better to call it an infinity metric space, whatever. But in any event, we had discussed this. I had mentioned this theorem. I'm not going to prove it, but it's still true. It turns out that this too is complete. Just like with reals, Cauchy is equivalent to convergent. Which means that if I can show that the sequence of partial sums is a Cauchy sequence, then I would be done. And that's what I'm going to do. Okay. It suffices to show that S sub n is a Cauchy sequence in the metric space, or relative to the C0 metric. Okay. So if I were to fix an input, because the C0 metric is the sup over all such expressions, first I'm going to take an x, try to bound that, and then I'm going to optimize over x's. That's sort of like a standard method. Then I'm looking at this. Well, this is nothing but f sub k of x added from n plus 1 to n plus p in absolute value. Okay. Now, putting the absolute value inside, this sum could only increase. But then each of these terms is bounded by the C0 distance of the corresponding function. So this is bounded. Let me write it here. By k from n plus 1 to n plus p of f sub k C0 norm. But I am assuming that the numerical series consisting of the C0 norms is convergent. We had discussed how that implies that the partial sums for this is Cauchy, which means that for any epsilon, there's an n such that for any n after that n and for any p, this is bounded by epsilon. Okay? So let me write it here like this. Such that for any epsilon, there's an n, such that for any lowercase n after uppercase n and for any p, this happens. For any x, okay. Well, but then if I were to fix everything else and optimize over x's, that would give me that the C0 distance between S sub n and S sub n plus p is bounded by epsilon. And that's what I needed. You see the tail, functional tail, is bounded by epsilon for a sufficiently large n. That means that this sequence of partial sums is Cauchy, which means that by the completeness of the function space, it has to converge to something. Converging in the function space relative to the C0 metric is the same thing as converging uniformly. And that's the end of the proof. Any questions? We have about 10 minutes. Maybe we can finish early today a little bit. Let me see. Now the next thing is to talk a little bit about power series. Maybe I should give you some preview. A power series is a certain type of functional series. Namely, you look at powers, or monomials, let's say, up to some numbers. So let me just define that. Power series is a formal functional series of the form let's say a sub n. Here, x star is some real number that you fixed, and a bullet is a sequence of real numbers. Because it turns out that especially power series of this form are intimately related to functions, more general functions. For instance, if I were to choose x star to be 0, and perhaps a sub n to be 1 over n factorial, that gives me the expansion that we know for the exponential function. And there are many other things, of course. We did 1 divided by 1 minus x, and you can come up with expansions of many other functions. And in a sense, a good way of thinking about these power series is that this somehow incorporates all infinitesimal information of a function near x star. Maybe I should start at 0 actually. Better to start at 0. So this expression then is this: a0 plus a1 times x minus x star plus a1 x minus x star, a2 squared plus a3 x minus x star cubed, and then all of what? X minus x star to the power 4. Well, it should be probably to the power 3 actually here. If you're using little o, I need to use 3 there, because then it's the 4th order, 5th order, and so on. Now, as you see, if I were to plug in x equals x star, then all of these terms are going to vanish except a0. So somehow, if I could guarantee that this thing converges, let's say uniformly, so that it gives me an actual function, then it would be the case that this is the value of the function at x star. And we've discussed this plenty times. Then if I were to get rid of these terms, this would be the linear term. So somehow this would be related to the first derivative. And then somehow this would be related to the second derivative, this to the third derivative, and so on. So if this is f of x, this should be f of 0, or rather f of x star. And probably I should call this. Okay, so when we were discussing this stuff in the context of differentiability, instead of looking at this, we looked at x star plus h. So that's sort of like a change of variable you need to do here. Here I'm imagining that x star is fixed, and x is a point that is sufficiently close to x star. So that means that x equals x star plus some h, where h is very small. Okay, so this is f of h. Then this is h. This is h as well. This is h. Somehow, this should be f prime of x star. And then here, we had seen this in the context of 1 divided by 1 minus x, instead of having f double prime of x star, because when you differentiate it ultimately you would like to be able to differentiate the series, if it makes sense, you would like to be able to differentiate it term by term. This is going to create a factor of 2. So you want to cancel that out, which means that a sub 2 should probably be f double prime x star divided by 2. And then this should be f triple prime of x star divided by 3 times 2. In other words, 3 factorial. And so on. Okay? So next week is going to be all about understanding what is happening here. If it happens that, let's say, my function is once differentiable, I won't have this full series, but at the very least, I'll be able to go all the way up to here. If my function is twice differentiable, then I'll be able to go all the way up to here, and then here, and so on. And then, if a function is so that I have infinitely many derivatives, and the series converges, then it's like, that's real analytic functions. That's the best type of functions in a sense, but also very rare, of course. Okay, we're going to spend some time. So the finite approximation, we're going to learn how to chop it off here, and then we're going to learn something about the convergence of this. Okay, and that's going to be Taylor approximation as well as analytic functions, and that's going to be the end of the class. Okay, thank you. That's it for today, this week. I'll see you next week.